So, thank you for the organizers for putting all this together. So, I'm here, probably one of the few exceptions. I'm a theorist. So, I was thinking when I got the invitation what to talk about. And then I remembered that just 1 year ago, Bob was in Erlangen, and he asked me, you know what SU11 is? So I spent almost half my life working in SU11. And he asked me, can you explain to me in a very simple terms why SU11 has this super resolution? And I said, no, I cannot. So we need to have some crosstalk, okay? And then I was thinking that probably, the best thing is we need to communicate each other in a simple term. So as a theorist, we live in Hilbert space, but we want to present results in something which is a phase space. And I want to present in 10 minutes a guide for the commuter. What is the... So, this is the famous sentence by Sir Peres, okay? So quantum phenomena don't occur in Hilbert space. They happened in the lab. So the question is how I pass from my Hilbert space to the lab. And then for that, there are, of course, in the end, you have to give probabilities. But also, it's nice when you picture quantum mechanics. And for that, probably the best thing to do is to use what is the Phasespace method. So the Phasespace was probably is as old as quantum mechanics. So I want just to present few slides how to go from one to the other, okay? So, and the idea is just to represent quantum mechanics, not in Hilbert space, but as a statistical theory in Phasespace. And so in that way, you don't have any abstract concepts from group theorists. It's simple to understand. Everything's like a fluid, okay? It's simple to picture. You can get very nice pictures. And it's computationally efficient. So in few words, what we need to have a phase space formulation of quantum mechanics. Well, first of all, we need to have a phase space. And this is a big, misunderstanding. There is a lot of people who is talking about the quantum phase space. There is no such a thing. Phase space is just a manifold. It's the way you describe things, which is quantum or classical, but there is no quantum phase space, even if it's regularly claimed in many textbooks. So we need then to have a way in which we pass from Hilbert space to functions. So we need a way in which we represent states as functions, okay? So we need to have distributions in phase space, but then realize that, we know that in quantum mechanics, operators don't commute, but functions are commutative. So we need to introduce, in a way, this non-commutativity of the quantum world in this function. So this is the role of something which is called the star product. So I'm not entering in any of those details. Let me just for a few, this is the only slide in which I have equations, okay? Let me go to the example of phase space for the oscillator, for continuous variables. Everybody knows that, so we know that we have coordinates and momentum, and they don't commute. So this is in, group theoretical terms, is called the Heisenberg-Weil group algebra. And then the first thing we need is to do what is the phase space. Of course, there are very sophisticated methods to describe this in a very compact way. But the idea is, of course, X is unbounded, P is unbounded, so the phase space is just a plane. And now the question is, what can I do in phase space? So I can just apply the exponential of X. It's not working, okay? And I know that the exponential of the P operator displaces in X. The exponential of the position operator displaces in P. So I can displace in both directions. So this means that I can have a displacement operator, which is, in physical terms, what one can control in the lab, the displacement operator. So then, if I can displace in phase space, the idea is what I want to displace. That depends on what you want to do. But probably for the oscillator, everybody knows that we displace the vacuum. Because the vacuum has good properties, minimum uncertainty states, and all that, okay? So essentially, these coherent states are just photocopies, displaced versions of the vacuum. Now the question is, well, now I need to represent the states. And this is my recipe for the commuters. So I represent the states by the Wigner function. More or less everybody knows about the Wigner function. The idea of the Wigner function is the average value of something, but then I can go from the Wigner function, from the density operator to the Wigner function. I can go from the Wigner function to the density operator. This is the two-way, the guide for the commuter. And this is the recipe, the only thing I want to discuss, how I construct this quantizer. The recipe is just you take the Fourier transform of the displacement. And this works for everything. Okay, let me give you a couple of examples. Okay, so first, this is the traditional way of representing the Wigner function. Okay, so this means that this is the phase space, X and P. But of course, a classical state is just a point. A quantum state is represented by a Wigner function. And we know, that there is this typical contour which represents the noise which is inherent to the state. So this means that the typical sentence, the uncertainty principle prevents to have a single point in phase space. This is where the nature of quantum mechanics enters into play. Okay, so this can be applied to any system, okay? And then the first thing we need to learn is that we have plenty of systems in which one has to choose properly the phase space. Here there is a huge community of people doing orbital angular momentum. You can think in the orbital angular momentum as just the same as position and momentum, but it's a position which is angular position, a momentum which is angular momentum. Formally, everything is the same, but there is a subtle difference. And it's that now the angular position is periodic. So that means that, the angular momentum is unbounded, but the angle is periodic. So you fold the plane, and then the proper phase space is just the cylinder. However, it's strange to have a picture of the orbital angular momentum states in the proper phase space. This is the typical state. So this is the cylinder. Of course, the angle is in one of the directions. The angular momentum is in the other. We have all the good properties. However, people like to present things like that, phi and L. And this is completely unnatural from a point of view. These are just cut states for these systems, okay, superpositions. So there is one thing that I want to draw your attention. Of course, we know that there's a common sentence to say that negativity of Wigner function is a very clear sign of non-classicality. Well, I think this is a very strong misunderstanding. So every Wigner function is, by definition, almost everywhere negative. There is nothing intrinsically important in negativity of the Wigner function. Only for X and P, one can show that for pure states, negativity of the Wigner function is non-Gaussianity. Is what you are looking for, that's okay. But don't try to extrapolate this non-negativity to other systems, okay? And even more than that, we can do the same for for spin, for a qubit, for SU2. And then the phase space, natural, I mean, we have this relation, which means that the natural phase space is the Bloch sphere. And you see in all quantum information to plot a qubit like that. But we learned that you cannot plot a quantum state as a single point. What's the point in representing a qubit like that? Cannot be. Where are the fluctuations of the qubit? Where is the minimum? So this means that we need to, again, compute the Wigner function for this and plot things in the proper way. This is a density plot. This is from an experiment of Wolfgang Ketterle, in which you have the density, I mean, this is the Bloch sphere. You have like a bump there. So this means that the state is mostly concentrated in the x-axis, but has fluctuations. And again, how can I construct the Wigner function? The recipe is the same. You Fourier transform the displacement. And the displacement operator, for example, for polarization, is just wave plates. And one word of caution, I mean, this Fourier transform in the plane is just making expansion in terms of plane waves. When you are in the sphere, the natural bases are spherical harmonics. So you make that, and you have this kind of representation. But then I come back to my first question with Bob. What is SU11? Can I explain that? And then immediately I realized that everybody should have been working on what is the Wigner function, what is the proper way of representing states for SU11. And that was not the case. So I was looking in the literature, and I found that some years ago, Miguel Alonso published a paper with two good friends, I mean, George Bogosian and Bernardo Wolf, just trying to do this problem from the classical point of view. But the paper was almost unnoticed so far, okay? I don't know why. So the idea is, what is SU11? Essentially, is more or less like SU2, but you change the sign of one of these guys. And then if you change the sign of one of these guys, you go from the sphere to the two-seated hyperboloid. So this means that the states live in this hyperboloid. And then you can construct the Wigner function much in the same way. You Fourier transform the displacement. And the displacement for SU11 is just squeezing. You Fourier transform squeezing, and you get these nice pictures of a coherent state in this is Ulrich Seifert who did this. So this is the Wigner function of a SU11 coherent state. And what is there is, of course, you can project, and you have in the unit disk this nice representation. So going back, you cannot represent a single qubit as a single point. You cannot represent a SU11 as a single point. Just use phase space in the proper way. And with that, just as I join everybody to say happy birthday, Bob, thank you very much.
Thank you for such a beautiful talk. My general comment is that you gave a very, very high-level theoretical physics talk that I almost understood.
Oh, thank you.
And Troy, I speak for many people here. Just one technical question, maybe go back one slide. You said this is the Wigner function. Is it the one on the left, or is it the one on the right?
Well, it's just a density plot. This means this. Yeah.
Thank you. I may say something about SU11. The first time I think I gave a presentation about T number, and that was the place that I talked about SU11. And there is a painting, very famous one, Escher, right? If you look at Escher, it starts to map everything inside of a circle. And the geometry that you have is exactly that geometry.
So this is the basic of hyperbolic geometry.
Now, I'm trying to relate this to the nonlinear interferometer that Masha and other people are working on. This is abstract. And you had mentioned that the SU11 interferometer gives you reduced noise. How do I look at your Wigner function and tell that there's reduced noise?
Because if you compare, for example, with the noise in SU2, so the noise is just the width of this Gaussian. The sphere has positive curvature, but the two-shifted hyperbola has negative constant one. So this means that, oh, sorry. This means that this Wigner function has, yeah.
It's narrow.
Yeah, always narrower.